Let's pick up with benzene and its derivatives. This is a guy named Kekulé, well, a cartoon of a guy named Kekulé, and it's kind of funny, but maybe you'll get it sometime. But this is called Great Events in Chemistry, just moments before his brilliant insight into the structure of benzene. I'm going to leave it at that because I feel like when you explain a joke, even if it was funny, it's not funny anymore. So maybe you'll get it. However, Kekulé had a really hard time, and so did anybody else, figuring out the structure of benzene. Benzene is an aromatic compound. Though there's this rule, this Huckel rule of aromaticity, and there's other aromatic compounds, but we're going to focus on benzene. So in this class, we're going to talk really only about C6H6, which has this structure with lots and lots of unsaturation. So it contains any compound we're going to talk about here, an aromatic compound, is going to be one that contains a benzene ring. Also known as an arene, which is a term that we use to describe aromatic compounds. Benzene has the formula C6H6. So the structure of this compound was a puzzle because it had so much unsaturation that it didn't undergo the typical reactions that double bonded compounds undergo. So Kekulé actually proposed two potential structures, which I'll show you on the next slide, that he said we're going quickly and they were switching back and forth between each other in rapid succession. So in benzene, all of the bonds are 140 picometers in length. So this single bond is 140 picometers. And this double bond is 140 picometers. Now, typically, a single bond is longer, and a double bond is shorter, and a triple bond is even shorter than a double bond. If you remember, they're like springs. The more we add together, they can't pull as far apart. So these bonds, this single bond that we have in this structure and this double bond that we have in the structure being the same length, tell us something about the structure, that it's not a single bond and it's not a double bond, but yet it's falling somewhere in between the length of a single bond and a double bond. Also, all of the bond angles in this molecule, so the angle between the hydrogen and this carbon here, that is 120 degrees. And here is 120 degrees. And here is 120 degrees. Everything is 120 degrees. And the structure, if we were to lay this flat, is flat. It is planar, so it fits in one plane, not like my drawing, because remember my drawings are not very good, but the structure lies in the same plane. CnH2n minus 6. C6, H 2 times 6 times 6 would be 12 minus 6 makes this a 6, C6H6. So what does it mean by two structures in rapid succession? It means this structure, let's say if we were to number the carbons here. That can't have two numbers, that's what I meant to be. Okay, so if we numbered these two structures, we notice the double bond here is between 1 and 2. Here it's between 2 and 3. Here it's between 3 and 4. Here it's between 4 and 5. And here it's between 5 and 6. And here it's between 6 and 1. But those double bonds aren't really there. In fact, this is a really special structure and has a cyclic conjugated system, and these are going to exhibit very special stability. So they're going to actually resonate. It's called a resonance structure between these two structures. It means it's rapidly switching from this structure to this structure. It's going so fast that it actually has special properties. And why is that happening? Well, if you remember how we're making those double bonds is using these singly occupied atomic p orbitals that we have. They all have that one electron in there, and that is going to allow us to have this pi system of electrons above and below the ring, where these electrons are going to be free to move throughout that area, and they're going to support each other, essentially. So they're delocalized. They're not localized on any carbon. They're going to move throughout the structure as a whole and help stabilize it when it needs to be stabilized. So benzene does have double bonds, but it does not undergo the same reactions that other double bonded alkenes undergo. So each carbon has that unhybridized p orbital that helps make up the pi system. That would look something like this. So these are the p orbitals, and this is the pi cloud above and below the ring that are formed in benzene. We do have some non-systematic names that you're going to get to memorize. Aren't you lucky? We love memorization, right? So these are our non-systematic names you do need to know. We've already talked about phenol. When there's a methyl group on a benzene, it's called toluene. When there's an amine on a benzene, it's called aniline. When there's an aldehyde on benzene, it's called benzaldehyde. When there's a carboxylic acid on benzene, it's called benzoic acid. Now this is new, huh? These two are kind of weird looking. So we have some weird things going on here. We have a benzene ring. This is essentially toluene, right? But there's this weird OH coming out of the middle of our benzene ring. What does that mean? Well, what that means is you can have what's called, I'm going to number these, okay? 1, 2, 3, 4, 5, and 6. You could have that OH attached here at carbon number 2, or it could be attached at carbon number 3, or it could be attached at carbon number 4. Now, if it was over here, that would be carbon number 2 again, and this would be carbon number 3 again, and this one's always going to be carbon number 4 because it's opposite. These are also known as ortho, meta, and para. So you could have 1, 2, or orthocresol. You could have 1, 3, or metacresol, or you could have 1, 4, which is known as paracresol, and the same for xylene. So if we take this toluene with the benzene and the methyl group, and we put another methyl group on it somewhere, it'll be called xylene. It'll be called orthoxylene, metaxylene, or paraxylene. Now, a lot of times you'll see an S here. That's not like when we go to the Walmarts and people just incorrectly put an S at the end of it. It's Walmart, not Walmarts. But in this case, it would be xylenes because it's mixed. That means it's mixed with all three, ortho, meta, and para. If these groups are present, you need to use them as the parent chain name. So you do need to know these. You should make cards and start learning them. If benzene is monosubstituted, we name the group before the word benzene. So we're just going to name the group chlorobenzene. Simple, right? This is a nitrobenzene. Ethylbenzene. Very simple. You pause it and try it. All right, so you're pausing it, so I'm going to keep going. This is going to be bromobenzene. And next we have, what is that big group there? We have T-butylbenzene, or tert-butylbenzene. And here we have a methyl group. Was that methylbenzene? Well, technically, but it's also known as toluene. So I want you to say toluene. If your benzene is disubstituted, this is where you're going to see where I'm talking about these names, ortho, meta, and para. So if you have a disubstituted benzene, you're going to name the groups in alphabetical order. So that ABC thing we've been talking about, right? So the first group is going to be named at position number 1. So A would be position number 1, B would be position number 2. Number 1, number 2, oh sorry, number 2, 3. 1, 2, 3, 4. And remember, we can't go put a group here and put a group there because then this would be number 2 and this would be number 3. So it depends on which way you number it is where the substituents are. So ortho is often just a little O. Meta is a little M with a dash, and para would be P. And everybody knows that that means ortho means it's on substituents 1, 2. Meta means the substituents are at 1, 3. And para means the substituents are at 1, 4. Now, any special group like toluene, phenol, aniline, benzoic acid, and benzaldehyde, it's going to always be number 1. So if there's a methyl group, that methyl group is going to be number 1 because it's going to be toluene. Okay, if there's an alcohol, it's going to be a phenol. All right, so let's give it a try. We're going to use ortho, meta, and para, or we can say 1, 2, or 1, 2. Which way do we go? This is bromo, and this is a carboxylic acid. Looks like this. This is why we had to memorize those functional groups at the start. So which one gets number 1? Well, benzoic acid is a special group, so we say 1, 2. We'll say 2 bromobenzoic acid or ortho bromobenzoic acid. Now here we can have, let's eraser, not a pen, 1, 2, 3. We could have 1, 3 dimethyl benzene, or we could have, this is meta xylene, or we could have 3-methyl toluene. So there's a couple words, couple different names here. 3-methyl toluene is also there. Here we have a chloro and an ethyl. So if neither of them are special groups, like in this case, we're going to go in ABC order. So in ABC order, which one will come first? We need to write the alphabet down. That's what it seems like lately, right? C comes before E, so it's going to be number 1. So 1, 2, 3, 4, para, or we can say 1, 4. 1 chloral, 4 ethyl benzene, or para-chloroethylbenzene. That's a mouthful. Why my pen's not working? There we go. So para-chloroethylbenzene. It's like speaking German. Again, you just stuff all the words together. Please pause it and try it. Oh, so this one, we have bromo and ethyl. They are ortho to one another, so that would be 1 bromo, 2 ethyl benzene, or ortho-bromo-ethylbenzene. We have a nitro group that looks like it should be special. I want you guys to note this. It looks like it should be special because of aniline, but this is not aniline. It's a nitro group. So this actually would be meta-nitrotoluene or 3-nitrotoluene. Trinitrotoluene. Something like this. Well, I don't have to do that. It's actually right next to it, right? So what is trinitrotoluene? TNT, dynamite. Where are they? Where are the nitro groups? Why don't you look that up? It'll be kind of fun. I'll let you do it. All right, the next one we have para. We have 1 and 4. So we have 2 chlorine groups. It would be 1,4-dichlorobenzene or para-dichlorobenzene. So that's how we use the terms ortho and para. Now, if we start adding more groups, like we see in TNT, or we have more substituents on the ring, we can't use ortho, meta, and para anymore. But if a special group is present, it's always going to be number 1. So here, it doesn't look very special, right? But methyl is going to be number 1 because that makes it toluene. So 1, 2, 3, 4. Here we have our phenol. So 1, 2, 3, 4, 5. Then, okay, so let's name this one first. I didn't finish that one. So we have toluene, we have 2 nitro and 4 chloro, but chloro comes first alphabetically, so 4 chloro, 2 nitrotoluene. Here we have bromo, bromo, and bromo, so 2, 4, 5 tribromophenol. Tribromophenol. Then here we have a nitro group, a bromo group, and an ethyl group. Are any of them special? Nope. So if none of the substituents is a special group, we number the groups to give the smallest set of numbers. So I could say 1, 2, 3, 4, 5, 6. I could say 1, 2, 3, 4, 5, 6. Or I could say, where did I not do? 1, 2, 3, 4, 5, 6. So the red ones would give me 1 ethyl, 2 bromo, 4 nitro. The purple one would give me, let's see, 1 nitro, 3 bromo, and 4 ethyl. So 1, 2, 4 looks better so far. This one looks better. All right, and what's the green one? The green one would be 1 bromo, 2 ethyl, 4 nitro, no, sorry, 5, is it 5? 5 nitro. So 1, 2, 5 or 1, 2, 4? Well, 1 and 2 are the same, but 4 is going to win out, so we get that 4. The red one is going to be the correct one. So we see, I'm just going to erase all. Here we go. 1, 2, 3, 4. We have 2 bromo, 1 ethyl, 4 nitrobenzene. That's how it's done, folks. Now, remember a benzene ring can also be a substituent. So I was very careful when we learned the term phenol, and I said I would correct your saying of this because phenol and phenol are very different. So phenol is actually when we put a benzene ring as a substituent. So when a benzene ring is a substituent, the group is going to be called a phenol group. So this is a phenol group, and it's going to be derived from removing a hydrogen from benzene. So this particular compound here would have a phenol substituent and an alkene. Well, this is going to be the parent chain, so we're going to say 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. And why are we doing that instead of using this one as our parent chain? Because we need to have this alkene in there, and we don't want to have 2 numbering systems. So that's why we do anything really, is to avoid 2 numbering systems. So 4 phenyl, 1 pentene. All right, we have the phenyl group, then we have 1 phenyl cyclohexene. Why did I give you that one? Well, I will tell you, a lot of people, now that we learn benzene, are going to confuse cyclohexane, cyclohexene, cyclohex anything with benzene. Benzene is special. It has to have those 3 double bonds or it doesn't react like benzene. Now, I see this less commonly, but you can also write C6H5. This would mean that it's also a benzene ring. So you can see any of these ways of writing the benzene ring as a substituent. So this would be 1, 2, 3, 4. It would be phenyl, comes on number 4. What do you think it is? 4 phenyl, 1 butene. Good. Let's talk about reactions. So benzene doesn't undergo the reactions that our typical alkenes undergo, but it does still undergo some pretty important reactions. All benzene reactions are going to require a catalyst in this course that we talk about. So nitration, halogenation, and sulfonation are just a few of the reactions that benzene undergoes. We're going to stick with a simplistic version of what benzene does in this case. So nitration, we're going to use to place a nitro group on the ring. Nitro groups on benzene rings become very explosive. It's a lot of fun if you do it in a controlled environment, or very helpful if you want to blast through a mountain sometimes. But we need a catalyst. So this is sulfuric acid. Now, I will not ask you to do things that are too complex. You're only going to be able to need to give products. So products for reactions of benzene with no substituents or those that are monosubstituted. And even then, I'm kind of skipping a couple steps because we have these things that are called ortho, meta, and para that go on the ring, but we also have ortho, meta, and para directors. And I'm not going to get into all of that and which ones will form, so I'm going to want you just to show me all possible products. Now, if you go into chemistry, you're going to take some more organic and you'll learn all about that. But because we're only a half semester on this, we can't go into everything. So we're going to end that one with just showing me all the products. So why don't we try one? All right, so let's look at something like this. And I'm going to show you a shorthand too for benzene. You might see people write it like that. So let's say plus nitric acid with sulfuric acid. What would we get? Well, we would have to draw 3 possible products. What do you think they are? Okay, this is what we're starting with. And we're adding a nitro group. Ortho, meta, and para. And then you could name them. In this class, we're probably going to have to do a lot of naming if we're going to be doing the tests online. So let's try one. The naming here would be, this is toluene, right? So we would have 2-nitrotoluene or ortho-nitrotoluene. Here we have 1,3 or 3-nitrotoluene or meta-nitrotoluene. And here we have 4-nitrotoluene or para. I'm going to give you one to practice. I want you to try this one on your own, so pause it and try it. Okay. Handwriting's not that good right now. So pause it, try it, give me the products and name them. Ortho, meta, and para. Right, so we would have nitro and bromo. Because neither of them is a special group, the bromo is going to get the smaller one here because it's going to be in ABC order. So we would have 1 bromo, 2 nitro, benzene. E-N-E today, I can't spell. I'll put this one in a different color so that we can see it. Here we have 1 bromo, 3 nitrobenzene, and here we have 1 bromo. I can't. Okay, I erase this. My hand. This table is very small that I'm working on. Let's try and do this. 1 bromo, 4 nitro, benzene. That says benzene. Okay. Now this one could also be 1,2, which is ortho bromo benzene. This one could be meta bromo benzene. And this one would be para bromo benzene. There you go. All right. What's another reaction that benzene undergoes? Halogenation. So halogenation is going to place a bromine or a chlorine on the ring. So iron 3 bromide or iron 3 chloride are used as catalyst in this case. So benzene reacts with chlorine with the iron 3 chloride to produce chlorobenzene and hydrochloric acid as a byproduct. This is what type of reaction? Because we have this byproduct, we know that it's a substitution. Plus, we have to get rid of something off the benzene if we want to put a chlorine on. So we can use chlorine, iron 3 chloride, or bromine and iron 3 bromide. Sulfonation places an SO3H group. Look at your shampoos, folks. I am very sensitive to sulfur, and this is called a sulfonate. So there is no water byproduct. Some books have this as an actual byproduct, but it's not. It's in the book in error. So there is no water here that comes off. Where H2SO4 is going to be used to catalyze the reaction to put this on there. So what this is this is a sulfonate, and this is going to be ending up in your sodium dodecyl sulfonate. We're going to have this hydrogen come off, and then put a sodium in there, sodium, and then we add dodecyl, which ends up, being. But that's what that ends up being later on when we are talking about long chains being on there. So now we have a sulfonation that's happening to this benzene ring. Now, why might we do this? Again, this is what I'm saying. So we have this is dodecyl benzene. Dodecyl benzene is going to get treated with sulfuric acid, and then we treat it with soap. Dodecyl is very long chains, 10 carbons on there. Then when we do this, we're actually, this hydrogen I just showed you that comes off because we have that OH group there. That hydrogen is what we call an acidic hydrogen, and it can come off, and we have this negative sign. That was actually a bond, but I just made it into a negative sign. And it's going to attract the sodium ion, and that's where you get sodium dodecyl benzene sulfonate, or SDS, which is a detergent. Look in your shampoo bottle tonight. Look in your body wash bottle. Look at anything that's in your shower, most likely, unless you've gone sulfur-free. You've got one of those in there. Now, some of our rings have other atoms in there. If there's something other than carbon, it's called a heterocyclic aromatic, meaning that it has a heteroatom, another atom, a different atom. Typically, it's oxygen, nitrogen, or sulfur. Yes, son, that's right. Don't worry, I'll be here all semester. All right, so this is pyridine. It smells like rotting fish. This is pyrimidine. It smells more like rotting fish. This is purine. Getting a trend here? They all smell really, really bad. This is furan. Why do we have these things? They're so smelly. They're gross. These should look familiar to you. They're all over in your body. They're all over in everything because these are the bases for DNA and RNA. They're the backbone part of it. So DNA and RNA. Do you remember which ones? Oh, don't worry. If you don't now, you will soon. This is for A and G. And this is going to be for T, C, and U. Uracil. Okay, guys, just making sure you're paying attention. We'll see those again. Don't worry. Phenols. Phenols are a benzene group with that OH group as a substituent on the ring. Phenols have many different uses and are common building blocks that we're going to see throughout the semester. So some of these are very common. and are known by their common names. You don't have to know the specific common names on here, but you might see them when you're out, so we're going to just go over them. This is 3-methylphenol, and it's known by metacresol. And this is what gives the chemical creosote its antibacterial and insecticidal properties, but that also gives it its toxicity and its ability to irritate bare skin. So not so nice. 1,2-benzene diol is known as a catechol. We're going to see some things called catecholamines when we talk about these later. So we'll see this backbone, and I'm going to ask you if you remember it, so give that one a star. But about half of this synthetically, produced synthetically, is going to be used in the production of pesticides. And the rest then is used for the precursor, the starting material, for fine chemicals like maybe those ones that are used in pharmaceuticals or in perfumes. Now, this is a very common building block in organic synthesis, so we're going to see that one again. Resorcinol. Resorcinol is used in, what is it used in? Skin treatments, for acne or to remove hard, scaly, rough types of skin. Hydroquinone is used to lighten dark patches. So these are a lot of skin. So those might be caused by hyperpigmentation, liver spots, freckles, age spots, those things people call them. But those dark spots of skin, this can be used in what they call like skin bleaching treatments to try to lighten those dark patches of skin. And that's it for our chapter on benzene and its derivatives. I hope you were enjoying yourself. I'll see you again soon.